Module 2, Section 2.2, Graphs and Transformations. Objectives. Objective 1. Become familiar with the beginning library of elementary functions. Objective 2. Transform functions using vertical and horizontal shapes. Objective 3. Transform functions using reflections, stretches, and shrinks. Objective 4. Evaluate and graph piecewise defined functions. Here is a list of 6 elementary functions. Identity function f of x equal to x. This is how the graph will look like. The domain is all real numbers. So this R means all reals. The range is also all reals. Square function h of x equal to x square. In this case, the domain of the function is all real numbers and the range is interval 0 infinity. Q function m of x equal to x cubed. The domain is all real numbers, range is all real numbers. Square root function, in this case the domain is all positive reals and the range is also all positive reals. This is the graph of the absolute value function. We write it like this. Transformation of graphs. If a new function is formed by an operation on a given function, then the graph of the new function is called a transformation of the graph of the original function. Graphs of both y equal to f of x plus k and y equal to f of x plus h are transformations of the graph of y equal to f of x. Vertical shift. The graph of y equal to f of x plus k can be obtained from the graph of y equal to f of x by vertically translating the graph of the latter upward k units if k is positive and downward absolute value k units if k is negative. Here is an example of vertical shift. We have the graph of y equal to absolute value of x, which is this graph, and we do have two transformations on that, like y equal to absolute value of x plus 4, which is the same as f of x plus 4. Because f of x is equal to absolute value of x. The graph of f of x plus 4 will be obtained from the graph of y equal to f of x by vertically shifting 4 units. So this will be the graph of absolute value of x plus 4. So the graph of y equal to absolute value of x minus 5 is obtained from the graph of y equal to absolute value of x by vertically moving it down 5 units. Horizontal shift. The graph of y equal to f of x plus h can be obtained from the graph of y equal to f of x by horizontally translating the graph of the latter h units to the left if h is positive and absolute value of h units to the right if h is negative. Here is an example. We have the graph of y equal to f absolute value of x, which is our f of x, and then we have the graph of y equal to absolute value of x plus 4 can be interpreted as f of x plus 4, y equal to f of x graph. Then when it is y equal to f of x plus 4, the same graph will be horizontally shifted to the left 4 units. So every point will be moving to the left 4 units. And if we are looking at the graph of y equal to absolute value of x minus 5, which will also be interpreted as f x minus 5. So the graph will be moving to the right 5 units. So the graph of y equal to x minus 5 will be this one. Objective 3. Reflection, stretches, and shrinks. The graph of y equal to a times f of x can be obtained from the graph of y equal to fx by multiplying each y coordinate of the latter by a. If a is greater than 1, the result is a vertical stretch of the graph of y equal to f of x. If 0 less than a less than 1, the result is a vertical shrink of the graph of y equal to f of x. And if a happens to be negative 1, the resulting graph is a reflection in the x-axis. Here is an example. y equal to absolute value of x, which is the graph indicated in black here. If you take y equal to 2 times absolute value of x, which is taking this form 2 times f of x. This was our function y equal to f of x. So the multiplying number is 2, which is greater than 1. So the graph of y equal to 2 times absolute value of x will be obtained as multiplying every y coordinate of y equal to absolute value of x by 2. Y equal to 0.5 times absolute value of x. So this time the multiplying number is between 0 and 1. So it will be a vertical shrink. So this is that graph. We need to get the graph of y equal to negative 2 times absolute value of x. We already have the graph of y equal to 2 times absolute value of x. So if you multiply that with the negative 1, this will be a reflection about the x-axis. So if I draw the graph of this function here, it will be shaped like this. Summary of graph transformations. Here is an example. We need a graph y equal to x square, y equal to x square plus 3 and y equal to x square minus 4. Notice that the graph of y equal to x square plus 3 can be obtained from the graph of y equal to x square by a vertical shifting, and also y equal to x square minus 4 is obtained from the graph of y equal to x square by a vertical shifting. We are going to use a calculator to graph these three functions. So we get the three graphs where the vertical shifting is indicated. Here is another example where we are looking at the horizontal shift. Y equal to x square will be the base graph, and this is like f of x plus 3, which is a horizontal shift, and this is like y equal to negative fx, that will be a reflection. So if you start out with the graph of y equal to x square, so this is the graph of y equal to x square, so this is going to be the graph of y equals x plus 3 the whole square. Now if you are looking at y equal to negative x square, that is obtained as the reflection about the x-axis. If you reflect this about the x-axis, we are going to get this graph. Here we are going to use the calculator to graph those three functions. So these are the three graphs. Here is another example. The graph of the function g is formed by applying the indicated sequence of transformations to the given function f. Find an equation for the function g and graph the function g. So the function fx is given as f of x equal to square root of x. The graph of f of x equal to square root of x is shifted 2 units to the left and 3 units vertically down. These are the two transformations. If the graph is shifted 2 units to the left, then the formula will be changing like this. 3 units vertically down means that f of x plus 2 will be changing as f of x plus 2 minus 3. So if we do these two transformations in sequence, our formula for gx will be g of x equal to root of x plus 2 minus 3. Objective 4. Piecewise defined functions. A piecewise function is a function whose definition changes depending on the value of the x variable. Here is an example. The absolute value function can be defined as absolute value of x equal to negative x if x is less than 0 and is equal to x if x is greater than or equal to 0. Procedure to evaluate a piecewise function at a certain value. 1. Determine which domain your value fits into. Substitute the value of the variable into the expression that corresponds to this domain and simplify. Example. Evaluate f of x when x is 0, 2 or 3 for the following piecewise function. F of x equal to x square if x is less than 2, f of x equal to 6 if x equal to 2, and f of x equal to 10 minus x if x is greater than 2 and x is less than or equal to 6. X equal to 0 is less than 2. Therefore, we need to use the first formula for computing f of 0. So, f of 0 equals 0 square equal to 0. That's how we get f of 0 equal to 0. When x equal to 2, the function formula is f of x equal to 6. So, the value at x equal to 2 is simply 6. When x is 3, 3 lies between 2 and 6, which means it satisfies the last condition. So we need to use the formula 10 minus x to compute f of 3. So when I substitute x equal to 3, we will get f of 3 equals 10 minus x will be 3. So 10 minus 3 equal to 7. So that is this value. This is the graph of this piecewise defined function. Notice that when x equal to 2, the value of the function is 6, which is this single point up here. The circles here means that the points are not part of the graph. Here is another example of a piecewise defined function. F of x equal to 2 minus 2x if x is less than 2 and is equal to x minus 2 if x is greater than or equal to 2. And notice that the point 2, 0 is included. This is 2, 0. And the point 2, negative 2 is not included. In this example, we need to graph the function f of x equal to 3 minus 2x if x is less than negative 1 and equal to x minus 2 if x is greater than or equal to negative 1. Here we have two pieces. We are going to graph those two pieces together in the same window. So let's take the first one. And this is a linear function, so we can graph that by plotting 2 points on it. So let's say x equal to negative 2. When x equal to negative 2, we will get y equals 3 minus 2 times negative 2, which will be equal to 7. That is the point negative 2, 7. Now we can also take x equal to negative 1 even though it is not part of the graph, and that is going to be a boundary point. So when x equal to negative 1, I will get y equals 3 minus 2 times negative 1, so that will be 5. When I plot that point, x equal to negative 1, y equal to 5, that will be plotted here. But notice that x equal to negative 1 is coming from the second inequality. So I need to select this as a circled point. Then what I'm going to do is I'm going to join these 2 points and getting the straight line. But I can only draw the line for x less than negative 1. So that means I need to draw the line to this side. So this will be the graph. Now going to the second formula, which is also a linear function, I'm going to calculate 2 points. When x equal to negative 1, I can calculate y as negative 1 minus 2, which is negative 3, and plot that point. Negative 1, negative 3 is here. And because x equal to negative 1 is part of the second formula, I need to include this point in the graph. So we are not going to use a circle there, we are going to use a thick dot. And then another value for x. I can take x equal to 1 or maybe x equal to 2. When x equal to 2, y is going to be equal to 2 minus 2 equal to 0. So that point will be 2, 0, which is plotted on the x-axis. So that part of the function has got a graph which is a straight line going this way. And this time we are drawing the line only for x greater than or equal to negative 1. So taken together, we will get the graph of the piecewise defined function. Here we are going to use the calculator to graph the same function in the previous example. This is how we are going to enter the function in the graphing calculator. To get the inequalities, we look under test, which is second math. Then pick the right inequalities. X less than -1. So which will be item number 5, -1. Then add a plus sign. Give the second piece, which will be x minus 2 with the condition x greater than or equal to -1. Again, the inequalities will be under test. Second math. Greater than or equal to will be item number 4, -1. Close the parenthesis. So that enters the piecewise defined function. Now we can select a window, something like -10 to 10 for x, with x scale equal to 1, and -10 to 20 for y, with a y scale equal to 1. If I press graph, I will get the graph of this piecewise defined function. But notice that there is some unwanted line segment here, and we can actually hide that by setting the calculator in the dotted mode. So I'm going to press mod and then come down here, put the calculator to dot mode instead of the connected mode. Press enter. And if I go back and graph again, I will get the two line segments. This is the graph of the piecewise defined function, which looks like what we got earlier. In this example, we are going to calculate values from a piecewise defined function. So we are given hx defined through three pieces: -3x minus 9 if x is less than -8, and is equal to 5 for x lying between -8 and 5, and equal to x plus 7 for x greater than or equal to 5. Let's calculate h of -10. So that will come out to be 21. If we want to calculate h of 2, 2 will be satisfying the inequality -8 less than or equal to 2 less than 5. In other words, 2 lies between -8 and 5. So I have to use the second formula. H of 2 will be the constant 5. If we want to calculate h of 5, I need to find out where 5 lies in these three intervals. So this says that x is greater than or equal to 5. So 5 is actually satisfying that criteria. So it comes from the third formula. 5 plus 7 equal to 12. So that is the answer there. And h of 9, so because 9 is greater than or equal to 5, we need to go by the third formula here. Again, x plus 7. X means 9. 9 plus 7 equals 16. So in computing a piecewise defined function at a given x value, we find out which of the conditions will be satisfied for that x value, and then use the corresponding formula for computing the function. Here is one last example where we need to graph a piecewise defined function. This time we are getting three pieces, and we are going to use the calculator here. And as we had seen, we can enter this function in the calculator as shown here. And if I put the calculator in the dot mode and use these selected windows, this will be x minimum, this is x max, this will be the x scale. And for y minimum, we select 0, y max as 95, y scale as 5. With this window parameters, we will get the graph looking like this.